Alrighty. Hello. Today, we'll start the first lesson of an introduction to statistical learning for big data. It's a fancy, it's a fancy title to say AI machine learning. Okay. Um, because ultimately the core, which drives the power of AI, is correlative data and statistics. So the data that we put into AI models is the data that we're going to get out. If that data is biased, the model will be biased. If it's high quality data, then it'll be accurate, high quality outputs. Um, so while model architectures and things of that nature can grow and advance, the quality, type, and amount of data that is fed to train these models is, as we'll see throughout this course, is of the utmost importance and probably an area where we would need to see, well, not need to see, but it would be helpful to continue to develop efforts to capture uh, additional quality data or higher quality data. All right, so this scroll wheel is a little bit annoying. Oh, I can use these buttons on the side. Forgive me, I'm autistic. Oh, I can go into read mode too. Look at that. All right, so what about statistical learning? Statistical learning refers to a set of tools for modeling and understanding complex data sets. Statistical learning theory is a framework for machine learning, drawing from the fields of statistics and functional analysis. And then machine learning would be an example of statistical learning, um, where we're using the correlations and metadata about a set of data in order to infer things about it or apply it to future instances of data. A little bit more about the specific example of machine learning. It's a science of where we get computers to act without being explicitly programmed. We don't set and hard code rules. We give computers pixel values or tokens of words and parts of sentences, and it determines the correlation between various words or between pixels, and it can generate new data or infer things based off of its previous knowledge. It's a technique of data science to help computers learn from existing data and allows for forecasts. And this can be used in my area of expertise is the visual, like computer vision, camera, high quality data, super resolution images and shit like that. I don't have as much practice with large language models. I did take a data, no, text mining course, um, where we learned about information retrieval systems, and then later got into a little bit about how tokenization occurs and like a lot of, I guess, the theory behind um, how language models are trained. A little bit about machine learning terminology. Samples. Samples are just the instances of data that you feed into your model, and these are used for training and testing of your model. Goodness me, these pop-ups are insane. My the features of a set of data are a sets of attributes represented as a vector associated with the sample. So in the case of images, your features your features of a sample are literally like the pixels. And the so each feature is comprised, or each pixel is comprised of an RGB value, and we learn things based off those number values. Labels. These are values assigned depending on the type of machine learning you're doing. These can either be categories, specific instance names, things of that nature, and are usually referred to as the ground truth. Their values assigned to examples. And in the case of supervised learning, what is referenced during the calculation of the cost or loss during training of a model. Here we have the output, the prediction made by the model, which is then leveraged against the ground truth or the label. So you have the output minus the label. You square that, and you have mean squared error is a typical loss function um, that's used to determine the accuracy. How close is that model, the expected value of that model to what's being output. Then you have the model itself. It's the information that the machine learning algorithm stores after training. These are typically in the forms of weights or neurons. Neurons. I'm sure there'll be a photo in here somewhere of what a neuron is typically looks like. A little bit more machine learning terminology. You have the training sample or examples that are used to train, and then you have testing samples. And typically in training and testing, let's say I have 1,000 images. You're gonna the the exact proportions are up for debate, but typically what we see is anywhere from 60 to 80% of those images are used for training exclusively, and then 20 to 40% are used for testing and validation afterwards. So in the case of 1,000 samples, of course, it would be 6 to 800, and then consequently 200 to 400 for testing. How does machine learning work? So first we select data and split it into various groups, training, validation, and test data. You then have model data. You model it and you use the training data to build the model using the relevant features. Okay. This is the training portion, right? And then you validate that model. You access the model with your validation data. You provide feedback to the output and hone in on like various weights. We then tune the model, improve performance of the algorithm via different features such as hyperparameters. This is typically things such as the learning rate, dropout rate, which we'll get into later. And we use the model and then can continue to test the model and its output in real world instances. Oh, why did that go backwards? That was strange. I hit the forward arrow in it. Yeah, why does that go back? Okay. Example of a machine learning task, self-driving cars. That's all video analytics and AI. How can you accurately predict demand for your product? Oh, that's okay. I don't want to get into the marketing side of things. So a little bit about everything we just covered. Machine learning uses historical data to make predictions. Machine learning is also similar to data mining, but data mining is the science of discovering unknown patterns in data in relationship. However, machine learning applies previously inferred knowledge to new data to make decisions in real life applications. Um, but usually in the process of applying machine learning, we do data mining because how do we unlock this previously inferred knowledge or known knowledge or whatever? Through data mining. Um, a great, a really common unsupervised method of learning um, would be like k-means clustering algorithms. And this is a data mining practice where we cluster data without knowing anything about it. We don't like a human hasn't gone through and assigned labels, right? Just remember that terminology, labels to the data. It's just the raw data and it's grouped together based off its raw, unknown patterns and characteristics. And then those clusters can be fed into machine learning model. Okay. So we've done the data mining to get the initial clusters. Then those are used, that data, those original clusters are applied into a machine learning model. And then now we get to the machine learning part where, let's say, a new data instance. I have four groups. I have Shakespeare. I shouldn't have done literature because I don't know fucking authors. J.K. Rowling and F. Scott Fitzgerald. What fuck? What's one more? Because I don't know who wrote the Bible. And then you have Muhammad because he's the fucking Quran, right? You have these four categories, and I give you a new piece of literature. What the fuck else did I give you the well, who did I just name? Fuck. I give you another like something else in the Harry Potter series, right? Because Rowling wrote. Oh, god damn. Let's not do books. Let's do music, all right? Say I have four genres: rap, rock, R&B, and gospel. And then I hand you a song by Nipsey Hussle. This is where the machine learning comes in, right? It looks at it and says, okay, I know that these four categories exist, and it's most similar to the data in this category. I'll insert it into the rap and hip hop section. It groups it. So machine learning takes a new instance and predicts future outcomes. Data mining unlocks patterns in data. When should we use machine learning? It's a fairly complex task that's computationally expensive. A lot of these models can get very large, and it's not always applicable to certain things. Whether there's an ample amount of data to train a model off of, can you formulate a problem clearly? Do you have sufficient samples? What is the overhead of going to label samples? What legwork will you have to do to clean your data repository? Um, is the problem a regular pattern or is it somewhat irregular and abstract? And then, of course, yeah, with any problem, how do you define success? So you kind of have these four quadrants of you can do something completely manual. You can code a complex set of rule-based algorithms. Um, so an example of this would be I just nest like hundreds of if statements. We've all seen those hilarious memes of the block of code when it's like my professor wanted me to determine if a number was even or odd. And the kid goes through and it's like on line one, if if number equals one, odd. If number equals two, then even. And they do it for every number down to 100. Now, obviously, this works. It accomplishes the task of finding all even and odd numbers based off an input from 1 to 100. Of course, that solves the problem. It's not efficient though, and it's not a universally scalable solution as it can only handle numbers within that range. Um, Now, granted, that's all you were given, but what if the scope changes in the future? Your code should be able to react to those changes. Um, but that's rule based. As this is a super long set of complex rules, adding new rules becomes very difficult. Once you kind of already have an architecture laid out, you have to make sure rules don't overlap and aren't conflicting. Rules can be difficult, especially as the system grows. Um, but at times this is appropriate. As the complexity of rules grows and the problem scales, we approach the need of machine learning. All right. This was don't let the formula scare you. That is the loss function that I referred to earlier. This is just mean squared error, where you have y hat Y hat, which is I my professors we always call it this Y hat. Um, I don't know if you're actually supposed to call it that, but for colloquial purposes, we'll call it Y hat is the expected value. That is the labeled ground truth value. That's the value I assign my data as the person that's building the model. That's what, let's say I input 2 plus 2 and I tell the computer it's supposed to be 4. I tell it it's supposed to be. That's my expected value. Let's say for whatever reason, the computer gives me a 3. That'll be the just the regular Y value. That's the output minus the expected. Okay. And then of course you have the average, the average squared error over the course of n number of samples. I hope you can see my cursor here. But this n is indicative of n number of samples. This could be 2 samples or 1,000 samples. It's how many times are we going to iterate over our sample set? Well, not how many times we're going to iterate over the sample set, but the samples in the set. Going through that, we take the sum, so all the errors that we get. So let's say there's a 3. We get a 3 for 2 plus 2. We know the value is supposed to be 4. The error there is 1, right? And then for the next one, let's say for the next time I input 2 plus 2, we still know it's supposed to be 4, but let's say it gives me 6. The yi value is 6 because that's the output minus 4, the expected value. The difference is 2. We then square that, which gives us a 4, right? And let's just say there's 2 samples in this entire set of data. 2 samples in this entire set of data. So n is 2. So the first time we input a value, we got 3 with an error of 1. Next time, we got an output of 6. We know the ground truth is 4. So that's an error of 2. But now we square it, mean squared error. We square it, and so that's an error of 4. It penalizes the model more significantly the further you get away from the ground truth. Those errors are larger as you move further away from the expected value. Okay. So you have one. So then we sum up those errors. We just add them. Now, if you do this, if there's 1,000 errors, if there's 1,000 samples, n equals 1,000, you have to sum up 1,000 numbers. For this example, it's just 2. So you have 1 plus 4. Those are the 2 errors that we've had. We get 5. Divide that over, and now we move to this side of the equation, right? So this is just a summation sign. Nothing scary there, just a summation sign. Bitch. And then 1 over n. This is the same as dividing by n. I don't know if you guys are math. I don't know. I don't fucking know. I don't know how on what level to explain this at, but hell, I'm just gonna ramble. Skip this shit if you don't need it. Um, 1 over n divide by n. So you have the sum of the error, which was 5, and then you divide by n. There were 2 samples, like we said, n equals 2. So divide by the number of samples. 5 over 2, 2.5. The mean squared error of the output was 2.5. We just calculated this mean squared error. That was a bit of a complex. This sometimes is really easy to get intimidated by math, but sometimes just take a step back, understand its parts, and it makes total sense. Collecting data. It's always important. Do we have sufficient samples? It requires a large amount of data. There's the reason this course is called statistical learning for big data. You gotta have a lot of data. There are data augmentation techniques that you can use when you have small amounts of data. such as rotation, translations, and flipping of images. All these things allow you to, let's say I only have 5 samples, but each sample I reflect or flip over the y-axis. So now it's inverted. Let's say each time I rotate 90 degrees, that's another like 3 different samples you can have. So that those 5 samples quickly turn into 15, then quickly turn into 30. And now we're because of data augmentation, um, we can generate sufficient samples. Generally, the more data, the better the performance, just because it allows the model to generalize better. If I were to ask you to identify a gun, guns come in all sorts of shapes, colors, calibers, sizes. How can you identify a gun reliably? This is a very abstract, constructed problem that we're facing. Of course, it seems somewhat intuitive to me, but what makes a gun a gun? Um, Let me just for the sake of um makeshift gun images. Just because I don't want to get flagged by the FBI. I want to see like some of the ones that I saw in Croatia, in Croat. These are all still fairly gun-like. Oh no. Oh, here. Let me reshare my screen. Give me just a moment. Okay, so you should be able to see my Google thing now. Um, you wouldn't classify this as a gun. Probably not. But this is a form of gun. I think it's called a slam stick or slam shotgun. You put a shotgun. There's a small nail in the back of the one of the pipes. You can slam it, and it'll act as a barrel of the gun. You have the firing pin back here. It's not activated via a trigger, but a kinetic energy that you supply, and it becomes a gun. So even you, how can we begin to classify something that comes in these various forms? This is it's a very complex problem. Ooh, I'll turn off my video. Okay. It's a complex issue. So we want the model to be able to generalize the best that it can. Um, let's see. Each example must contain 2 parts. The features or attributes of the example, and then the label or the answer that you want to predict. Your data needs to be somewhat regular. Machine learning, it learns regularities and patterns. Um, it's difficult to learn patterns that are rare or irregular. Um, and this goes back to the abundance of data issue. If something is a unique or very rare phenomenon, there's often not a lot of data behind it because I mean, it's rare. So that of course there wouldn't be that many measurable instances of it. It could be hard for a machine learning model to accurately detect that anomaly or that rarity, you know. Um, but there are other ways that we can do it. So if there are outcomes that are very regular, if it doesn't necessarily, so we could detect an irregularity by not detecting a regularity. But to simply train off something that like detect this anomaly. Well, it's anomaly. It's hard to measure in the first place. Um, anyway, yeah, there are clever ways that we can get around certain things. Representations and features. Machine learning algorithms ultimately operate on numbers. We have to find a way to enumerate our data. How can we represent a vector of words as numbers. We tokenize each word, we assign, we find a way we can count word instances and come up with word counts throughout the book. So let's say the word the appears 1 million times throughout the book of Harry Potter or some shit like that. Um, yeah. So how do we evaluate success? Machine learning optimizes the training criteria. The evaluation function has to support the business goals. I really don't like this slide, but okay. So as we train, our accuracy settles at a certain level, about 94% in this example. And as we test and improve our model, those two values should reach acceptable levels. And it does somewhat depend on the business goals. If if I need a speedy recognition but can sacrifice accuracy, then of course that's fine. But if I'm using like weapon systems or targeting systems, this needs to be highly accurate, little room for error, things like that. Of course, model accuracy and the business goals where this is being applied will affect the threshold of accuracy that you need and the how you evaluate success. So when should I use machine learning? Ultimately, when the problem is large and complex or abstract, and when handwritten rules are just not sufficient. We'll end that here. I think I've kind of yapped for long enough. We'll go over the rest of chapter one later.